Nonlinear oscillation creates something which we call as chaos, and this is where we'll be discussing for this video, in which we'll be discussing about the chaos theory as well as the nonlinear oscillation. So before we get started, please consider liking and subscribing, and also please check the notes in the description for the notes throughout this entire video, as well as the timestamps for you to skip throughout this video as well. So let's just get started with a very simple introduction. So previously we discussed about the harmonic oscillation or damped driven harmonic oscillation. It has a form of mx double dot plus a function of x dot plus a function of x equaling to a function of t. And so in here we see that there are three different components. There is the position, there's the velocity, and as well as time. But this is not always easily solvable. Like normally it is pretty chaotic, but it is not random. So we need to differentiate between chaos as well as random. So random is non-deterministic, while for non-deterministic, while chaos is deterministic. So this means that if you know each of the initial conditions, you can actually predict what's going to happen. But a slight change would result in a very different type of motion. And so this is what we call as chaos. So we can just jump straight towards the nonlinear oscillation. Nonlinear oscillation. So we'll just do like some examples first. If we have force equal to negative kx, this is the normal harmonic oscillation. But we should try to consider if we have another component in which it's an x cube. So we can determine what's the potential energy. You could just take the first integral and take the negative. It will be kx squared over 2. This is the potential for a spring, for an ideal spring, and epsilon x to the power 4 over 4. So if you try to plot this graph here in terms of the f and the x, as well as the u and the x, what you could see here is that if we have a linear oscillation, it should be, for the ideal oscillation, it would be something like this. But there are two different types of oscillations. One of them is something which we call as hard. So hard is when epsilon is less than 0. Or basically the logic is that it requires much more force for you to move it for the same amount. So we can see here that the force is higher. And then we also have something which we call as soft springs. So it's going to be something like this, in which the force that you need to move it is much more less. So we can also plot the potential energy. For hard, it will store much more potential energy, while for soft, it will just bring it to the side. So it won't require lots of energy. So that's basically the logic behind hard and soft springs. So let's go straight away into an example in which I have already programmed. So if we have something like this, you have a spring, mass, and another spring, we could try to figure out what's the trajectory of, no, sorry, the motion of this particle here with mass m and both sides k here. We can try to solve the equation of motion, in which I'll just skip through. But the way that we'll actually do this is actually just by taking this position to be y and this thing to be l. And let's say it has an initial position of d. We would be able to obtain that the my double dot is going to be negative 2 kd over l times y minus kl minus d over l cubed, y cubed. And so you could just do this by the simple equation of motions anyways. So this is what we observe. And this thing here is so if we try to compare it with the thing above here, like the force is negative kx plus epsilon of x cubed. So this is something in which it's indicating that epsilon is less than 0, or this is a hard spring. So we can try to solve this. So if we try to add, let's say, an external force, F0 cosine omega t, this could be simplified into, we'll just use x double dot in here. Negative 2kd over L, this is the spring constant, times, sorry, it should be this, in which this would be called as A, negative AY, and then we'll add it with a small component, epsilon x cubed, and also the force over the mass, g over cosine omega t. So this is a equation of motion in which it's nonlinear. You could see the nonlinear term here. And so the method for you to solve this is actually through perturbation. So this is a very good approximation. So the way that it works is that you just guess a solution. In here, a good guess would be cosine omega t, A times cosine omega t. And this will be our first guess. And so we can try to get a better result just by plugging in the x1, and we'll just later adjust. Because this is the solution when this epsilon is 0. So if we try to plug it in, hopefully it will have a very similar result. So trying to plug it in, we'll obtain negative A times A cosine omega t plus epsilon A cubed cosine cubed omega t plus G cosine omega t. And so you could actually simplify this and try to solve what is the x2. So this component here, we could just rewrite this as 3 over 4 cosine omega t plus cosine 3 omega t over 4. I mean, you could just derive it. And so if you try to regroup it, we would have x2 double dot to be 1 over omega squared a times a. Oh, sorry. So you would obtain this minus 3 epsilon a cubed over 4 minus g cosine omega t minus epsilon a cubed over 36 omega squared cosine 3 omega t. So we cannot really observe this very easily, and so in here I provide you with a simulation of this following the scenario in which we observe this oscillation between two different springs. You could see that the normal oscillation for spring is very different compared to this type of hard spring, in which it starts to deviate from the original harmonic oscillation. So that's the idea of soft and hard springs in real world situations. Like normally springs are also having they also have the hard and soft, but if you assume an ideal condition, you could arrange them in such a case that it will produce a hard or soft system. And some systems are also asymmetric. Like you could actually, instead of adding the epsilon x cubed, you could just add lambda x squared. And what would happen here is that if you try to plot this here, it would be something like this when lambda is positive. So we observe a hard system as well as a soft system here, depending on the direction. If you go in the positive x, it will be softer. If you go in the negative x, it would be harder. So we can also try to plot the u over x. It would be deviated slightly towards the side here. And this one would go higher. So the u here is kx squared over 2 minus lambda over 3x cubed. So that's basically some ideas in the nonlinear systems. And how do we classify soft and hard systems? And how do we solve soft and hard systems? Let's just go into the idea of phase diagrams, in which this is a very powerful tool, in which we have already discussed previously, and now it is a very powerful tool, since if you remember, x dot is plus or minus the square root of 2e minus u over m. So with this, you could just try to plot the x dot over x, right? And there are lots of different type of systems. Like let's say if you consider a hard or soft system. Let's consider a hard system first. For a hard system, it would be much more flatter like this. something like in here. These are called attractors. And there are also lots of different types of attractors. So let's give you one example. If we try and let's say do a van der Pol equation, so it's x double dot is mu x squared minus a squared, x dot plus omega 0 squared x equaling 0, what we observe is a attractor in which we will show here. So if you see here that there is a path on the outside and the path on the inside, and somehow it will go towards a cycle in which it will converge together into one singular path. This is what we call as the limit cycle. And a limit cycle is a type of attractor as well. So it's a very interesting thing for us to see that certain systems, even though they seem to be chaotic, but they still converge towards a certain oscillation. Let's show you another example in which this is what we call as a plane pendulum. So a plane pendulum is quite simple. So we would have a rod with length L attached it to a bob with mass m. And we'll just denote this angle here to be theta. So you could try to solve this by using by using Newton's law for angles, or basically the torque, or just use Newton's law. It also works. What you would get is theta double dot is negative g over L sine theta. And this is something which we have already figured out. This is omega 0 squared. This was something that we observed previously. Plus omega 0 squared sine theta is 0. So instead of observing or trying to solve this differential equation, we can just instead try to plot the phase diagram. So we can get the kinetic energy. It's half moment of inertia omega squared, or ml squared over 2 omega squared. And potential energy is just the height from the zero. So we'll call this to be 2 mgl. No, sorry. It's mgl 1 minus cosine theta. So we can just solve this and you would get the theta dot. Here, theta dot squared is 4g over L sine squared theta 0 over 2 minus sine squared theta over 2. You could just use certain substitutions. And by the way, theta 0 here is the maximum theta. So you would obtain something like this. Well, this is basically this is already giving you the phase diagram. But maybe you want to ask, what is the period of the pendulum? I mean, we have known previously that the frequency is square root g over L for very small angles. But what if the angle goes large? So you could do some substitution. So one of the most specific substitution in here is substituting that k is sine, no sorry, it's substituting that z is sine theta over 2. And we'll denote k to be sine theta 0 over 2. So you could try to plug it in and try to solve the equation of motion here. And what you would get is a very interesting type of integral. So let me just show you the end result. So after you have figured out what's the d theta over dt, you could just solve for the time. The time would be 4 square root L over g, integral from 0 to 1 of dz over 1 minus z squared, the square root of that, times the square root of 1 minus k squared z squared. And this is the elliptic integral. Elliptic integral. And so this is a very well-known equation, or a very well-known problem. And so people have already figured it out numerically. So you could just look it up into a table and observe what's the period for the particular cases. But anyways, if we try to consider very small k, we can just expand this guy to be 1 plus half k squared z squared plus some other terms. And if you try to do the integral now with the 1 over the square root of 1 minus z squared here, you will get a series in which it is in the form of 4 square root of L over G, pi over 2, plus pi k squared over 8, and so on, in which I would fully derive. But in here, we could just simplify this much more further. This would just become 2 pi square root of L over G 1 plus theta 0 squared over 16 and some other value. So this is basically the period. This is approximately the period for a plane pendulum. So what we can do instead is actually try to transform this phase diagram as well. So this phase function here, we could try to simplify it so that it doesn't contain any signs. So we'll just approximate it to be a very small value. So it would just become 1 over 4 the square root of L over G theta dot squared, and then you add it with theta over 2 squared is the same thing as theta 0 over 2 squared. So this is basically a Taylor expansion of this previous one, in which I've already reordered it as well. So you could simplify it and it would just become square root of L over G theta dot everything squared plus theta squared is approximately equal to theta 0 squared. And this looks like a harmonic phase path. So we have already solved lots of these. And so this would be plotted into something like this. If you would have something like this as well, you would see the separatrix here and here. So the separatrix is basically the point in which it is very unstable, so it can go towards the top or the bottom depending on the initial condition perturbation. So these are the separatrix, and at the center, as well as the other points here, because this is technically symmetrical, it's an attractor. This is a separatrix. So let's try to consider when it is exactly at the point where the separatrix exists. What we observe is that the square root of L over G, theta dot, over 2 is going to be the same thing as the square root of 1 minus sine squared theta over 2. So basically this is when theta 0 is pi as well. So you could just put it into the original phase diagram function, and you could simplify this to obtain that theta dot is plus or minus 2 square root of G over L cosine theta over 2. So it really depends on how you put the side. Is it going from the top side or from the bottom side? Now let's try to discuss something which is much more interesting, which is jump, hysteresis, and phase lag. So we'll just consider a harmonic oscillation with damping, but instead of actually only considering the simple case, we'll just assume that k is a function k0 1 plus beta x squared. Now this creates something which we call as the Duffing equation. So in here I tried to plot the trajectory of this Duffing equation, and you can see that there is a point in which it rises up and then it just by sudden drops, and then later it goes back up. And this is what we call as jump. And if you check the phase, it's going up like this, and then when it goes back down, it just drops. This is what we call as hysteresis. So this is a very interesting problem because we cannot truly explain it straight away because the equations are hard to understand. So we'll try to do a model. Let's just consider when we have this is f and this is x. We'll just consider something like this. It's piecewise, but there is two different spring constants. And so if you try to plot each of these uh, resonance curve, it would be something like this. There will be one here, and there will be another one here. So consider if, let's say, that this is A. What you would expect is that your trajectory should rise up, and then it would reach towards A, and it would start to switch gear. Like somewhere along here, it would go to the K prime region, and it would later appear somewhere along here, and it would just go to the peak. But after high frequencies, when it reaches this point again, it will drop back down towards the original K curve. So that's the trajectory when it goes forward in omega. But what happens when it goes in the opposite direction? Well, it would just go up here. It would just go up, go up, go up until it reaches this A, in which it would jump towards the K prime, and it will follow the curve, and then in here it would try to drop back towards the A prime. So there's a imaginary thing going on. Maybe it will just go something weird, maybe along here, but it would just go back to this original place. Now this thing here is the jump that we observe. And you could do the same thing for the phase. The phase is something like this, in which you would have two different curves. So this is the K and this is the K prime. So the forward sweep will go up and up until it reaches the point where it starts to change, right? And at this point of change, it would try to go towards the K prime region and following the curve. And then after that, it would go back to the K curve. So it would just jump back here, following this curve. But in the opposite direction, it would be following this K curve, and it keeps on going through until the point of the jump. It would just jump down and follow the curve and jump back towards the K again. This is what we observe as the hysteresis. So it's a very interesting phenomena that we see in a nonlinear spring constant. So this discussion is very out of the scope of technically this entire course, but it's a very useful idea to think of when you start to delve into the idea of chaos. So let's discuss about some more chaos in pendulums, maybe. Chaos in pendulum. So there are lots of different ways for you to create chaos. One of them is simply just add an external force going up and down, or maybe even do a double pendulum swing. You would know this a lot when you talk about chaos, in which a very tiny motion will create a very different motion. Same thing for springs like this. No, sorry, pendulums like this, or even if you have a pendulum and you apply some magnetic fields, it would have a very different path as well. So in here, we'll be discussing of a very specific problem in which you would have a pendulum and we apply a torque. You can just solve this, and simplifying the problem, you would be able to obtain that this is just x double dot equaling negative cx dot minus sine x plus f cosine omega t. So this is a second order, which is nonlinear differential equation. We can simplify it by actually denoting x dot as y. So we would obtain y dot is the same thing as negative cy minus sine x plus f cosine omega t. So what you would have here is two first order differential equation, which is nonlinear, but it's simpler for us to figure out. And so we can actually just put this into the phase space. So it's just y and x. So if we try to do this, in which I'll show here, you would see that there is this oscillation going on in which it is determined by the torque that you give. So in here, I also display 7 different values for this f here. So F is the magnitude of the torque. And what we observe is very chaotic behaviors. Some of them are much more controlled, but others are very chaotic. And how do you try to understand these types of motions? The idea comes from point care. So point care developed the idea just to create sections. So let's say if you have an oscillation that is going through x and y, but also in time. So it would be oscillating like this. So instead of trying to plot the entire trajectory in the phase space, you could just take a section, and each time it will be crossing a different point. So you could try to adjust the distance here. We'll just denote that to be 2 and pi. So if you try to plot for each of the 2 pi, or basically 1 radian of the entire change, technically it's 2 n pi over omega, what you would get is something as follows here, in which the motion becomes different points. And if the points are much more gathered together, it means that it is much more well behaved compared to a much more well spread point care section. Now let's try to discuss about mapping. So mapping is a tool when you do a something which we call as a iterative equation. So let's say xn plus 1 is a function of xn. This is basically the idea. This is what we call as mapping. So it goes from one point to another, and then it goes to another point, and it goes to another point based on the previous states. So instead of only considering one mapping, you could consider adding another function, another variable, and this variable would be used to create a map. So let's do an example. A very popular example is xn plus 1 is alpha xn 1 minus xn. This is what we call as the logistic function, or the logistic equation. So the way that you would actually do this type of mapping is that you could actually consider it in terms of a graph. If you have, let's say, this function here, this is the function of alpha x, and you could have the xn plus 1 equaling xn. If you have these two different functions, you could first start with a initial value. Let's say it's this one. This would be at x0. No, let's do x0, yeah. And so it will plot the function towards the xn plus 1. So this would be your x1. Now, from here, you would want to transform this x1 into your next initial value, which will go towards this point. So it will be starting at this value. This is the x1. So it goes here, and then if you keep on doing the same, it would be converging towards this point here. So that's basically the idea of the logistic function, and basically this describes populations. So in here, I'm going to show you the map for the logistic function. You could see this bifurcation. So this bifurcation shows that instead of having one stable point, you have two different stable points for some reason. So let's try to explain why there's like this splitting. So let's consider the same logistic map, but instead it's much more higher and it goes like this. So what we can do is that we can put a initial condition. It's going to go here, it's going to go up, it's going to go here, go down, like maybe it goes into this point. And this would go back to this original point and it would just oscillate between the thing. I mean, this is the most extreme value. But you would see that actually that it doesn't converge here. In fact, it will just diverge outwards like so. So obviously the way that I plot this is not that good, but if you actually do this with a better ruler, you would see that it will actually converge between two different points. And that's what we see with the bifurcation plot. Also, an interesting point is that actually the splitting between each of these guys here, the ratio goes towards a number which we call as the Feigenbaum number. And so I won't fully discuss what the Feigenbaum number exactly is, but it's basically the ratio between this one and this one. That's the Feigenbaum number. So let's try to identify chaos. Identify chaos. And the way that you do this is actually very interesting. So we'll take much more time to discuss about this identification of chaos. So let's say you have x0 and x0 plus epsilon. Obviously, these two will have some differences later on. So we'll just approximate the difference to be epsilon e to power n lambda. So this is the difference. So let's try to see. Maybe d0, if you plot this, it should be epsilon, in which you could also show that to be x0 plus epsilon minus x0. So it's epsilon. d1 is, well, you first put it into the function or your mapping, and then compare it with the mapping of the original one. This is approximately the same thing as epsilon df over dx at x0. And you could just extend this further. And what you would get is epsilon df n times over dx, something like this. And this is approximately the e and lambda. So we can figure out what's the Lyapunov exponent here. Epsilon would be 1 over n, sum of n minus 1 towards, from 0 to n minus 1 for the I, of natural log of df over dx, f of xi, there. And you just take the limit as n goes to infinity. This is the Lyapunov exponent. So something to note is that when lambda is less than 0, you could observe that the exponent will dwindle down. So this will converge actually. But when lambda is greater or equal to 0, this will diverge, or basically chaos. So I will show you the Lyapunov exponent for a logistic map. You would see that there are different dips, and this shows the stable configurations, while the one higher than 0 shows you the chaotic parts. And so this is basically a introductory episode for chaos. And so in the next video, we'll be discussing about gravity and leave behind everything to do with chaos. And so thank you very much for watching. Make sure to like and subscribe. And also please share this to your friends who wants to understand physics in a much more deeper understanding. Thank you very much, and I will see you on the next video.